before I get started, I did bring some toys for everybody to take a look at, so I passed these around the audience. I'll show you what I have over here. This is production hardware for the Legion Go OS. This is pre-production hardware, less stable. I have a Steam Deck. This is the regular one. This is a ROG Ally. So feel free to pass these around and take a look at them, do whatever you want with them. They're not all running SteamOS. Some of them have CachyOS on them, so they may or may not be stable. Feel free to play with them. No, not Bazzite. I don't like Bazzite for reasons that I can talk about later. OK. So let me go over some of my background. Today, it's my first time presenting at Texas Linux Fest. But I've been working on Linux in some fashion for about the last 20 years. I started out working in the Ubuntu community, packaging MythTV and getting involved with the MythTV project. Haven't really worked on it in a while, but it was a jump start to getting into the Ubuntu community. I started out working at Dell on shipping Ubuntu and Red Hat preloaded on hardware. When I started, we were doing it on maybe like 2 or 3 Inspiron products. And as we grew, we started to go across the whole portfolio. You might be familiar with the Dell Sputnik project, which was the XPS 13 Developer Edition. Did a lot of work on that, bringing that to market. The other big thing that I did at Dell that you might have heard of is the firmware update project. We were the first ones that kickstarted that project. Both me and Richard Hughes from Red Hat are co-maintainers for that project. And the very first machines that shipped it were actually Dell IoT gateways. I don't know if those are still shipping today, but it was the start of making sure we can get all the parts working for it. And it brought forward how we would do things on all of the client notebooks, workstations, et cetera. So it started out as a really small project, but now it's got hundreds of thousands of downloads. It's shipping on tons and tons of hardware, and actually intercepts some of the work that I did for the Legion Go OS as well. Another thing that I did when I was at Dell, you might have heard of, with systemd, there's a feature called Suspend then Hibernate. It's where you're able to put the machine to suspend and then program an RTC timer. You wake up after how much time you say, and if you haven't had any usage of the machine, puts it into Hibernate. So that's a systemd feature that exists now. Maybe you guys have used it. But so a lot of my work has kind of been a blur, similar to how Dustin had said that his hobbies and his professional life have intercepted. I hack on various Linux things on the weekend. Like I said, these various devices I brought, a lot of them before we did the Legion Go OS, I was just hacking on them myself to do whatever. But I started at AMD about 4 years ago, and my team at AMD works on enabling new technologies so that when you go and buy your brand new laptop, handheld, whatever, that it's going to be working on day one with Linux. We work closely with OEM partners like Dell, HP, Lenovo. I work closely with the framework team as well. If you have any of their laptops, they run great because we worked with them very early on. We get the early prototypes and enable everything properly. Within the different communities that I work, I specifically work in FWEPD. I also am a Debian developer and package a bunch of AI-related applications there. I package the FWEPD stack there. I'm a Ubuntu core developer, and so I work in Ubuntu wherever I can. And I'm a kernel maintainer for the AMD pstate driver and the AMD HFI driver, which are both power-related drivers for AMD hardware. I have lots of other people inside AMD that I work with on enabling hardware, but I will write bug fixes for any driver. I'm not sticking to one driver. And so I want to start by mentioning that I'm not a stranger to SteamOS. You guys might remember a while back, Valve announced the Steam machines, and Dell was the launch partner for that with the Alienware Steam machine, or the ASM 100. At that point, the SteamOS ecosystem was nascent. Game coverage was really spotty. We didn't really have Proton at that point. And it was a new concept that no one was really sure how well it was going to do. At that time, one of the things that I worked on was the kernel driver layer that controlled the LEDs. There's a little LED on the head, an LED in the corner. And so those LEDs can be programmed to whatever color you want. And I worked out the kernel driver that talks to the firmware to make this happen. And then that was submitted into the upstream Linux kernel at that time. And it still actually gets support today. I don't work on it, but other people have started hacking on it. They've added support for more hardware, and it was a good starting place. What happened was Valve did a shim layer between that driver and the Steam client. And so if it saw that you were running on the ASM 100, it would say, we're going to expose this new area into Steam client to program the LEDs to whatever color you want them to be. Then that was about 10 years ago. And between then and Steam Deck, there wasn't really anything that Valve had put out. But they took a lot of learnings from that product really seriously. And I mean, that's why Steam Deck came to market, and it's been so successful from a lot of those learnings And so let me talk a little bit about the Legion OS and what it takes to enable new hardware. So enabling new hardware with SteamOS starts well before the hardware's ever even been conceived. Before the first prototypes are even made, we have discussions about what components are going to be going into the hardware in that design. OEM designs are always based off of what's called an AMD reference hardware design. And picking the right components that are supported upstream or will be supported upstream is crucial for being able to get a product delivered on time. If there's components that are present in the OEM design that are missing from the reference design, we have to cross-reference the upstream readiness and find out where applicable, what the implications are for any software that uses those components to run that hardware. There can be a lot of software layers that interact with the hardware, so just having a kernel driver isn't necessarily enough. So during planning, it's really important that we think about how the software that supports the hardware works today, and then think about how it needs to change because of how this hardware design works. Once those initial plans are ready, the next step is to go through and do a bring up with the matching reference hardware with SteamOS. This is really important to do during planning because you have to make sure that there's not any insurmountable gaps that are going to jeopardize the schedule or the actual viability of the product. In order to give enough time to code new drivers or fixes and for those to land upstream, AMD attempts to upstream new hardware support as early as possible. Like I said, my team works on mostly Ubuntu and RHEL, and a lot of that hardware support we have there on day one with mainline kernels when the products hit the markets. So with all the planning out of the way, work streams have to be identified that are going to be going across companies. Schedules have to be made for all those work streams and matching milestones for those work streams. There has to be mitigation plans for surprises. There has to be contingency plans for if a work stream fails. And so because of that, you need to have a program manager that's going to oversee everything and make sure everyone is sticking to their scheduled milestones, everything is going on time. So often one of the most challenging aspects of development is how long it takes to actually upstream that code into the Linux kernel. Kernel releases take between 9 and 10 weeks, but you have to have code ready 6 weeks before that. You have to worry about how much time it takes to actually backport that code, if it can backport, if your base kernel is a lot older. And if you skip upstreaming or you don't leave enough time for that, those decisions can be building a house of cards that if you have user space software on top of it, could fall apart. If the interface that you use in user space is built on predication of a certain way the kernel works, and the kernel driver maintainer, subsystem maintainer says, no, I'm not going to accept that, now you have to rewrite all of your user space software. So to avoid those challenges, whenever possible, we try to upstream code to mainline. We submit those backports of those changes to keep that technical debt low in distro kernels like the SteamOS kernel. And so like I said, one of the very first things that we did after the Legion OS kicked off was to look at what it took to get SteamOS running on AMD's reference hardware. And so AMD reference hardware is what the OEMs use initially to design their products. Often they'll try to use as many common components as possible as the AMD design for better compatibility with their design. So before the first SteamOS samples or the first Legion OS samples were even ready, we wanted to make sure SteamOS could boot up and run on this reference hardware. As I mentioned before, AMD spends a lot of time upstreaming hardware support before the OEM prototypes are even created. We already use reference hardware with other distros like Ubuntu, RHEL, and Fedora. So loading SteamOS helps identify things that need to be ported specifically into SteamOS. And so to my knowledge, this was the very first time that SteamOS had been used outside the Steam Deck in any formal fashion. There were design decisions that Valve had made in SteamOS knowing that they were only running on a Steam Deck. And so we had to identify areas that we had to introduce abstractions or update to make the OS work well outside of a Steam Deck. And so we identified 6 work streams, you can see them mentioned up here, from the reference hardware, bring up that AMD and Valve worked on together, again, before we even had prototypes from Lenovo. And so you might ask, why do you even bother with putting this on the reference hardware? It's not going to ship with SteamOS, right? Well, the reason is it's important that if you run into a problem on any of the prototypes, that you have a baseline to compare in an environment that has extra debugging capability. You look at this board, I mean, it's got tons and tons of extra pogo pins. It's got tons of extra inputs. It has a postcode on there. It's got extra buttons. I have relays to control things on there. You don't get anything like that on any of the small little handheld devices. That's the one at my desk, actually. So AMD adds a lot of this extra debugging capability into the hardware. So if we can reproduce the issue on the reference hardware, we're much better equipped to solve it on that hardware instead. And so to give you an example of a failure that was a lot easier to debug on the reference hardware, was one of the very first things that we saw loading SteamOS was a black screen at startup. And so on the reference design, we're able to interrupt the boot process. we could see that graphics wasn't being set up properly due to an older snapshot of microcode that gets loaded onto the GPU. We put the updated snapshot of microcode into the OS image. We were able to get further along and start working on other problems that we found. Debugging this on a handheld, of course, it's not impossible. It's just going to be harder. You're not going to have a keyboard. You're not going to have serial outputs. It would just take more time. And so this, along with those other work streams I mentioned above, were areas that AMD and Valve had to get sorted out in advance of the first prototypes of the Legion OS even being produced. And so that brings me over to the Legion OS work streams. The Legion OS project was kicked off about a year before it came to market or so. And after our first few meetings to discuss the project, there was 5 groups of work streams that we identified to be sorted out. I already mentioned that we were focusing on the reference platform and what was involved there. We had these 4 other groups of work streams that were going to be unique to the Legion OS design. And so we jointly discussed all these work streams and figured out who needed to work on them. So let me go through that first work stream, the firmware update stack. So in SteamOS, all of the firmware updates are wrapped behind buttons in the settings menu. If you go into the settings menu and hit update, it's going to update your OS, update your client, it'll update firmware. It does it all at the same time. And that means that users don't need to know to go to find a firmware update. They just run updates in SteamOS and they just work. And the Steam Deck uses a collection of binaries and scripts that are intended specifically to that hardware. But the Legion OS has to support updates for its own BIOS, as well as for the microcontroller used for doing both of those 2 joysticks. Early on in our planning, this was one of the things we identified. And we produced a strategy that let us go and update the Legion OS, but also to let us scale it to any future products that we based off of a similar design as the Legion OS. And at a high level, the strategy was based across the FWPD stack. We would build all the updaters into that stack. And so for those of you that are not aware, the way that FWPD works is that you have a client like FWPD Manager or GNOME Firmware or KDE Discover that talks to a daemon, which is the FWPD daemon. And the client also talks to a server infrastructure. That server infrastructure is the Linux Vendor Firmware Service. And OEMs will publish firmware to the Linux Vendor Firmware Service. The client will download the firmware, pass it to the daemon. Daemon does the installation of the firmware. And so we had to work out the integration of how the stack would work in SteamOS, knowing that it's all hidden behind a single button. We, of course, had to wrap a client or write a new client. We had to get those new packages into Arch, the new enough versions, get those pulled into SteamOS. We ran into some problems that the FWPD stack was too big. Valve has very strict requirements about how big their OS image could be, and this was adding, I think, 25 megabytes. So we had to find ways to pare it down to get only what was needed into the SteamOS image. So now let me jump over to some of the specifics of what those were for the Legion OS. So the flow for installing a BIOS update, it starts with the Steam client. Steam client works with that unprivileged FWPD Manager client to reach out to LVFS, and it gets the updates. If there's updates available, it'll download the update, pass those to the daemon. The daemon will then stage the update onto the EFI system partition. And the EFI system partition is marked for the next boot that you will go and pull the update off of there from an application called fwpdx64.efi. This then calls into the BIOS itself for a UEFI runtime service called update capsule to apply the update. And it appears to be a pretty straightforward process, but we actually discovered some problems along the way with the SteamOS installer. Valve, because they were not doing BIOS updates this way previously, had a very small EFI system partition. And you have to have enough room to stage the update, as well as for the update to be decompressed while it's being installed. And so we realized that Valve had to modify their installer to make bigger EFI system partitions to support this update infrastructure. So now all of the SteamOS recovery images for Steam Deck or Legion OS or any hardware are bigger so that this infrastructure can still work properly. And so that's going to mean that, if we have a future device besides the OS, it will still work for BIOS updates in this methodology. And so the next thing we had to worry about was the microcontroller that's in the Legion OS. And this uses a update protocol that's proprietary to Lenovo. It's unique to that specific design. And during our planning discussions, we talked about the strategy. We said early on that we have to make sure that if Valve is going to be supporting them, that they have an open source update process. And so our strategy was to bring that in as a FWPD plugin and then bring FWPD in SteamOS. And so the team that owned this protocol, they were based in China, and the specification for how the update works, all written in Chinese. So before we could even get started, we had to get a professional translator to come and translate it so that we'd be able to work on it. myself. So once Lenovo got the specification translated, I was the one who did the FWEPD plugin for it. And so I wrote the plugin in a matter of like 4 or 5 days. It was relatively straightforward because the protocol includes signing on the infrastructure. As part of writing the new binary to the SPI image, it verifies signature, and if you mess up the flash process for some reason, it rejects the binary rather than break the device. It's really annoying doing development that if you're doing a device that's not signed, you'll brick it, and then you have to go and pull the hardware out, use dediprog to flash it again. It could be a very, very painful process. So once I received my initial prototype hardware, the plugin was already written at that point, and I just had to go and test it on the hardware and make sure that it worked. That took me about a day, and then at that point, we submitted the plugin for legal approval. We already have approval to submit to code to the FWEPD project for AMD, but this is Lenovo-owned IP, and so we had to get Lenovo's legal team to sign off on submitting this into the project. Once we had their approval, then we upstreamed it into FWEPD, and we waited for the next FWEPD release, and then we brought that downstream into SteamOS. And so you notice that the flow for installing the update, it's very similar to a BIOS update. The exact same button in the GUI is used, and the exact same lower layers will fetch the update and they'll stage it. The difference is that the plugin will be running in the OS at runtime, and what it does is it resets the microcontroller into a bootloader mode in order to flash the update. It applies the update to the SPI and sets it back into a runtime mode. When that bit's all done, it's able to be used immediately right after that without having to reboot the device. The net effect is if you hit that update button and there's a microcontroller update, your LEDs will flash on the controller saying that it's being updated, and then the controller won't work for a few seconds, or I think 15 seconds, come back, and then starts working again with the new update. Okay, so the next work stream that we had was for hardware abstractions. So some of those design decisions that were made in SteamOS were because it was only intended to run on the Steam Deck hardware initially. You know, they made a lot of sense at the time, but as new hardware is brought to the market, SteamOS needs extra layers introduced to manipulate that hardware differently. So what Valve did was they created a piece of software called the SteamOS Manager. It's open source software. Anybody can go take a look at it. It's on GitLab. It includes a stable dbus API, and it serves two purposes. Number one, there's a standardized interface for the Steam client to manipulate hardware and software. And that means that if you want to change the TDP, you would go and use this interface to say, change my TDP. SteamOS Manager will say, I'm on a Steam Deck, I do it this way. I'm on a Legion OS, I do it this way. The other reason is that they want to have a standardized implementation for a distro to provide an implementation. So if Bazite, for example, wants to bring in SteamOS Manager, they could bring that in, and however Bazite talks to the hardware, it could be done. So outside of the Steam Deck, Legion OS is the very first device to be supported by SteamOS Manager. And as SteamOS Manager gains support for more devices, appropriate abstractions will live there, and back implementations will be made for hardware features. If you go and look at some of the code right now, you'll see that there's code being submitted for the Claw, for the ROG Ally, the ROG Ally X. All sorts of other handhelds are starting to get support here as well, even if they don't have formal SteamOS support. So a major difference in how the Steam Deck and the Legion OS work is the input system, and this actually turned into a giant amount of work. So handheld input is a unique problem for desktop operating systems. Without the use of a keyboard and a mouse, traditional methods of having the OS respond to user control aren't really available. For devices designed around Windows, this generally results in two solutions. You have keyboard macros, or you have proprietary input devices. The use of the keyboard macros or proprietary input devices mean that there has to be vendor-specific software that creates virtual UI buttons to manage the hardware. It's not really a standard. You'll find ASUS does it this way, Lenovo does it this way, MSI does it this other way. The Steam Deck, however, is fairly unique in that a single vendor-developed input device provides all of the input data through a single HID raw interface. You get buttons, you get axes, touchpads, capacitive notifications, and a gyroscope, all from the same input device. The way that it works is the hardware is updating the entire state of the device in a single 64-byte HID report that runs at 250 hertz. Steam input then reads the input events and writes output events directly to the HID interface while the Steam client is running. There's a kernel driver called the HID Steam kernel driver that checks if Steam input has the device open, and if not, it can create a fallback event device descriptor with user space permissions for other purposes. But if you contrast this over to other handhelds, a lot of handhelds use off-the-shelf parts to make an input ecosystem. And typically, there's like an Xbox 360 style gamepad microcontroller, a separate AT keyboard, USB interface for macros, an inertial measurement unit, like a IMU for a gyroscope, and sometimes a pointing device or a joystick to mouse type of mode. The GoS is more similar to the Steam Deck in this regard, in that it only has 3 input devices. There's a HID raw gamepad with all the buttons on a single HID report. It also has an endpoint that picks up by the kernel driver XPad, but it's missing the buttons inside of the X input standard key set. The gyro itself is wired to the MCU, but it has a pass-through that exposes a HID raw interface as well. And this avoids pulling 6 channels on the IIO subsystem, because that's slow, but it also has a touchpad HID raw interface. And so in order to support this device, what ended up being done was modifications to bring Input Plumber into the SteamOS ecosystem. And Input Plumber is used to aggregate all of the various inputs provided by that IMU, the gamepad, the touchpad, and it blocks events from the XPad kernel driver. And it routes them all to a virtual Steam Deck HID device. And so this kind of leverages the maturity of Steam Client with what they call Steam Input. Input Plumber will emulate a Steam Deck by having this virtual device. And you can end up with things like haptic feedback, gyroscopic integration, paddle support, menu support, all of those kinds of things. And the way this is done is that there is a unique Valve product ID for non-Deck devices that Input Plumber will report. And that allows Steam to customize the UI and then do separate key binding databases that match the actual hardware. If you look in Steam Client on the GoS, you'll see that there's glyphs that match the actual buttons of the GoS that are different than what's on the Steam Deck. And that's because of this virtual HID input device. And so the Windows SKU of the GoS was actually brought to market before the SteamOS SKU was ready. This was the plan all along, but because of that, there was actually devices in the market that had different firmware for the touchpad, for the SteamOS version and the Windows version, as we were still working out a lot of the input specifics. So initially, the Legion GoS touchpad, it acted like a virtual mouse. It gave you relative positions and nothing that was like an absolute position tracking. Since there's no reference in relative mode, where in space an event is, there's no reliable way to translate the relative to absolute events. And Steam Deck interface requires absolute events. So to make the trackpad work like Steam Input, a new firmware was created to work on that touchpad. And it allowed switching between relative and absolute modes. This also required a microcontroller update because the touchpad's connected to the microcontroller to be able to send the configuration commands through the microcontroller to that new mode. So all the SteamOS models, if you go to Best Buy and buy the black models, those all have this updated firmware already, whereas the Windows models, which are the white models, they ship with the older firmware, but you can do an update to go and get the newer touchpad firmware. So a HID kernel driver was needed to interface with the microcontroller configuration interface. And this allowed things like Input Plumber to set the pull rate of the GoS interface to match the Steam Deck at 250 hertz. It also allowed enabling absolute mode at runtime when the driver gets loaded. That driver is not accepted in the kernel yet. It's still on the mailing list on Linux Input. Hopefully the next kernel cycle will get this in. But the exact same interface is what is used by fwupd for flashing the updates. And so what happens is fwupd and this driver will get along to coordinate the update process to make sure you don't have input going on at the same time as you're doing a firmware update. Okay, so with that hardware abstraction functionality out of the way, let me talk about what kind of power and performance optimizations we did for SteamOS. So the first area I want to talk about is the CPU performance. I'm in a bit of a unique position as it pertains to optimizing CPU performance. And that's because I'm the maintainer for both AMD P-State and the AMD HFI drivers upstream. And AMD P-State, it's an extension of the ACPI Collaborative Processor Performance Control specification. If you go to the ACPI spec, you can go read all about this and the details of how it works. But so what we have for the AMD P-State driver is basically an extension of that specification that matches how AMD hardware works. At a high level, the basic idea behind it is that the hardware will advertise the capabilities to the OS, saying that I can go up to this frequency, I can go down to this frequency, here's my preferred frequencies. And then the OS can indicate back to the hardware how it wants the workload to perform, either a performant workload or an efficient workload. And then it'll make that request to the hardware, and the hardware will be responsible for actually doing the adjustment to the frequency dynamically to meet that request on the fly. Each of the cores on the system can be supported to set whatever the preferences are. So you could have 1 or 2 cores that you want to be really performant, the rest really efficient. You could program it accordingly. And so outside of SteamOS, a lot of you with AMD CPUs might have noticed that there's been a big jump in performance around kernel And that's because I finished wiring up a concept called the AMD preferred cores into AMD P state. And so what this is basically when you do CPU manufacturing, there's going to be some cores that are going to perform better than others. For whatever manufacturing artifacts, you might have 2 in the corner in this corner of the die that work better than the other 14 in this side of the die. And so we have the capability for that hardware to advertise that information to the OS. And the OS scheduler can exploit this information when scheduling tasks to get better performance. The exact amount, it depends on the individual workloads. It depends on your individual CPU that was manufactured. But generally speaking, it could be between a 10 and a 20% improvement without a hit to battery. The Legion OS, it shipped with a 6.11-based kernel. And so this work was finished upstream, like I said, in 6.14. And so I worked out a backport from 6.14 to enable this feature. As a result of that backport, any AMD hardware that takes advantage of this feature will run better with this version of SteamOS, including the Steam Deck. Okay, next thing that we did was TDP tuning. And so within the Linux ecosystem, there's a concept called the ACPI platform profile, and this represents the power state of the system. In a traditional distro, it's exposed in the GUI, like in GNOME or KDE, as a system performance slider or a system power profile. And so there's a kernel interface that abstracts implementations from one to another. There's a link over to the kernel documentation you can look at later if you want. And on AMD reference boards and on some OEM designs, we use something called the AMD Power Management Framework driver. This is a Platform x86 driver. It was upstreamed back in, I think, like 6.8 or 6.9 or so. And this lets you do that static power slider as well as some other dynamic measurements. But on the Legion OS, there's actually an ACPI WMI-based interface that Lenovo offers for tuning TDP. And that's because on Windows, again, they have their own Legion Go software that they use to manipulate this interface rather than the PMF framework. And so this meant that we had to write a brand new WMI driver for manipulating the TDP. We found that after this driver was built, it didn't seem to work every boot though, and there's some sort of race condition that was going on. And in digging into it, the reason for that race condition was that it was racing with the PMF driver. Their hardware doesn't use PMF for this purpose, but still loads it. And so if you had PMF load first, you have TDP tuning not working. You have the Legion WMI driver loading first, it works fine. And so what we ended up doing was working out some set of changes upstream that allow multiple drivers to be able to load platform profile support simultaneously. What happens is there's a new class interface, and so if PMF registers first, it gets class 0. If Legion Go registers first, it gets class 0. But you still have the legacy interface available, and so you can write to one file, and it'll change all the drivers at one time. This also landed upstream in kernel 6.14. But again, SteamOS was using kernel 6.11. So this also meant that we had to do backporting of an entire stack of drivers, a lot of infrastructure changes. It was kind of a giant backport. I think it was like 90 patches that we had to backport for SteamOS to bring this in. But Valve was willing to do it because they wanted to have a successful product to market. Okay, so the last part of this was gluing it into the client. And so that meant that SteamOS Manager had to add support for manipulating this interface and then advertise that capability to the Steam client. If you look at the Legion OS sample tab going around, if you go into the quick settings menu, you'll see all these are advertised in there. You can pick those. The LED on the top of the Legion OS will change colors to match which state you're in. Okay. Yeah, so for me, I play Silksong all the time on the Legion OS. And I actually set this to the power saver setting because Silksong is not very CPU heavy. As a result, I can get better battery life on Legion OS by being in that power saver mode. Okay. Okay, so I hope that you could see that you can't really just expect SteamOS to work on the hardware originally designed for Windows without extra work somewhere. You need to go through the planning cycles. You need to go through all the extra development cycles to implement the support for the platform-specific firmware and the hardware. You need to make sure that there's enough time baked into the platform schedule to make sure that everything can be tested, developed, and upstreamed. Besides the planning that AMD, Lenovo, and Valve did, something else that Lenovo did was that they seeded hardware, pre-production hardware, into developers of the Linux gaming ecosystem. For example, I know the Bazite developer had some of this hardware early on. Derek Clark, who worked on Input Plumber, he had this hardware early on. And they were really smart to do this because it really made sure that we were able to get a successful launch. All of these people helped to bring this to a reality. And so with that, I want to open up the floor for any questions. set of repositories that you can work on, and you can do development images early on. So while we were waiting for that legal process to be ironed out, we did private builds, and we tested them on SteamOS to make sure everything was working properly.
It seems like there's going to be a natural iteration of the hardware all the time, but you're only able to design to what is the next most near release. So, like, how are you able to pass on lessons learned or new architectures or new sampling laterally to a team that doesn't have a project coming out that's 5 years after yours? Does that exist? Are you having to do them in sequence rather than simultaneously?
I mean, so if you look at the baseline support for AMD hardware, if you take the latest SteamOS image, it's going to work on Strix Halo, which is the latest hardware that AMD has. So if you have a Strix Halo handheld that comes out, it's going to work basically. You're going to be missing all of these things for TDP tuning, these things for how the input works, and those require development. And so it's going to require coordination of the designer of that platform with the either Valve or with the input plumber community to make sure that that gets smoothed out. I think that if there's another Lenovo design that comes out, it's very likely they'll use similar interfaces, similar designs. It's probably going to be a lot less work for another Lenovo design than it would be for this one.
You guys have to pay for it.
Yeah. Yeah, I mean, that's why a lot of the decisions we made, we wanted to make sure that they were scalable decisions, not a one-off thing. And that was really important to Valve as well. In those planning meetings, they wanted to see a vision that however we did everything, it's not going to be a one-off. Okay. Anything else?
I noticed in your slide you had squared up to kernel 16.14. Apparently in 16.2, real-time kernel functions were put in.
Mm-hmm.
Is there any need to move to real-time for any of this architecture? Since it is a game machine, it doesn't seem like it's necessarily necessary.
I would say it's not necessary, and if you did move to it, you're going to have a pretty significant battery impact from running real-time. And I mean, there's always this big balancing act of performance and battery and handheld space. And so it's a very fine line. Okay, thank you, everybody. Oh.
I learned the first time that the Steam input or the Steam TX input is all one interface versus other devices that have multiple interfaces at the same time.
Yep.
In your opinion, is it better to have one place, one interface for all the different types of inputs, or would you rather have this multi-channel approach?
I prefer all-in-one. I think it's a lot easier. You don't run into conditions that you have to aggregate, and you can have racing hardware. You can end up with devices running out of sync. I think one is way better to go if it's possible.